Hello and welcome to this video that goes through an AQA particle physics question. As part C, kaons are mesons that are produced by the strong interaction between pions and protons. The equation shows a reaction in which a kaon and a lambda particle are produced. So it's pi minus plus proton makes a neutral kaon plus a lambda particle, deduce the Quark structure of the lambda particle. So here we have, let's write down the structures of each of these quarks. So we've got a pi minus, which is going to be anti-up and down. We have a proton, which is up, up, down. We have a kaon, a neutral kaon, which is going to be anti-strange and down. And then we've got our unknown particle, which is the lambda. So from here, we want to, the easiest way to approach this question to start with is to do the conservation rules. So pi minus plus a proton makes a neutral kaon plus down. Not down, plus a lambda, neutral lambda. So in terms of charge, we know that it's going to be minus 1 plus 1, which is 0, makes 0 plus 0, which is 0. So the charge is conserved. But that doesn't tell us much because we already know that this must be neutral. The next one is the baryon number. So the pion is 0, it's a meson. Proton has 3 quarks, so it's got a baryon number plus 1. And on the other side, the kaon is a meson, so it's 0. So that means that for the baryon number to be conserved, we must have a plus 1 in terms of our baryon number. So therefore, we conserve it. So that tells us that this is made up of 3 quarks. Now finally, the strangeness. It is a strong interaction, therefore strangeness must be conserved. So the strange particles on the pi negative has no strange particles. The pion, has no strange particles. Proton has no strange particles, so it has a strangeness of 0. The kaon has an anti-strange particle, so therefore it must have a strangeness of plus 1. Therefore, the lambda particle must have a strangeness of minus 1 in order to conserve strangeness. So that tells you that the lambda particle must have a strange quark. So the next thing then is how do we find out what our remaining quarks are? So we've got anti-up, down, then up, up, down. And here we've got an anti-strange and a down, and then we've got a strange quark here. So in terms of how we can deduce this, we're looking for an overall charge of 0. So we know that the strange one gives us a charge of minus a third. And if we look here, we've got an up and a down quark that essentially not inside, we've got these two from the proton. Well, if we add the charge of the up and the down quark, it gives us plus 2 over 3 minus a third, which is equal to a third. And if we add that to our minus a third, we get a neutral one. So therefore, through logic, we can determine that the charge of the lambda 0 is going to be strange, up and down. And essentially the anti-up particle goes to an anti-strange particle, down to down, then the up goes to a strange particle, then up, down, and that is how you can deduce your quark structure for the lambda 0, for neutral lambda. We don't need to, again, the full details of how each one changes, you don't need to know. You just need to use the conservation rules and then deduce what the possible quark structure can be. So your answer here is strange, up and down.